Vectors. It says, for an example of what a vector is, consider two baseballs hit into the air as shown in the figure below. One is hit with an initial velocity, and that's your pretty much a starting speed. An initial velocity of 30 feet per second at an angle of 20 degrees. And you see that what's called a vector right here. It's hit at 20 degrees. Here's your horizontal with the ground. It's hit at 20 degrees at 30 feet per second. And the other is hit with an initial velocity of 60 feet per second at an angle of 45 degrees. And you see it in red from the horizontal. The length of a vector represents the magnitude. Notice that you had this first ball that was hit at 30 feet per second. Second ball hit at 60 feet per second. Notice anything about those vectors? The red one is twice as long as the blue one. The length of a vector represents its magnitude. The harder something's hit, the longer the vector. So the vector representing the faster baseball is drawn twice as long as the other vector. The direction of the vector is indicated by the position of the vector and the arrowhead at one end. So, to make a long story short, what you need to know, vectors have both size and direction. They indicate where it's going, and they indicate how fast it's going to get there. Vectors have both size and direction. Here you go, vector notation. All vectors have initial points and terminal points. Kind of like with the baseball problem, the initial point was where the ball was hit. The terminal point gave you the size and direction of where it was going. So the initial point and terminal point, for some reason I've not got those attached there. That B should be on the tip of that. Therefore, vector BA and AB are not the same vector. They're what's called, chopped out. They would be the same magnitude, but they're going in opposite directions. Vector BA and AB are not the same vectors. The way that you name vectors, like here, the vector that you have up here, which again, that bothers me really bad that that's not connected, that B is not right here. But the vector you have up here is vector AB. Starts at A. A is your initial point, and it goes through B. What vocabulary term from geometry is a vector? Remember that? It's kind of like a ray. Remember rays? A ray is a lot like a vector. The way you name a ray is the same way you're going to name a vector. When naming vectors, sometimes we'll use a bold letter. Instead, there we go. Instead of using the vector bar. Also, we can use a single letter to represent a vector. Well, you'll see that more as we go. Magnitude of a vector we've already talked about. Once we denote magnitude with what looks like an absolute value bar, and you see there the vector symbol, same as the ray symbol. Anytime you see absolute value bars around a vector, that simply means the magnitude. How long is the vector? Equal vectors, in order for two vectors to be equal, they must have the same magnitude and the same direction. Makes sense. Now, you got to be careful with that, though, because they don't have to lie on top of each other. Those two vectors looks like the same magnitude, because magnitude is the length of the vector. That tells you how hard it was hit. And they're pointing, even though they're not on top of each other, they are pointing in the same direction. They're pointing northeastwardly, and you can find that angle there. So just because it says magnitude direction does have to be the same, doesn't mean they have to lie on top of each other. So those two vectors could be equal there. Component form. Now the vectors we were just looking at had an initial point and a terminal point. So we really had 2 points incorporated, 2 points involved in it. Most of the time, though, we're going to be dealing with what's called the component form of a vector, where you're given a simple 1 point here, 2, 5, in vector bars. The component form of a vector, the initial point is always 0, 0, is always your origin, when it's in this component form. When written in component form, a vector closely resembles a point. We can see the horizontal and vertical components of the vector, hence the name. That's the reason we call it component form. Your component form here, or your horizontal component would be 2, your vertical component would be 5. The vector actually goes to the point 2, 5. Draw the vector, initial point 0, 0. There's the vector 2, 5. I want you to start thinking of it like this, though. Think about a good example is, I guess, kind of like the wind. Let's say the wind is blowing in that direction. Okay. When the wind is blowing in this direction, I want you to think of it. Actually, part of it is blowing in this direction, right? You're still going to be able to feel part of that wind blowing in this direction, but the majority of it will be blowing northernly. You got some blowing to the east, some blowing to the north, the majority blowing to the north when the wind is blowing here. You're going to be able to feel some of it in this direction. So when you have a vector, or you can think of it like this. Let's say that you're pulling something. You're exerting your strength in this direction. You're pulling something this way, and that's what a vector is. A vector is going to represent some sort of force, whether it be the wind, whether it be driving a car, whether it be pulling something, pushing something. A vector most of the time is going to represent some sort of force. If the force is being applied in this direction, well, some of your pulling power is going this direction. Some of your pulling power is going, actually the majority of your pulling power is going this direction. Okay? You can break it apart into two components, and that's the reason we call it component form. You're going to draw the following vectors in component form. 3, negative 2, and I'm not going to spend a lot of time on this. I think we're good with it. 1, 2, 3, negative 2. There's that first vector. Your second vector, negative 1, positive 4, looks like this in component form. And your third vector, negative 3, negative 2, 1, 2, 3, negative 2, looks like this. Any questions about vectors in component form? Scalar multiplication. And we've already talked a little bit about what happens when you multiply a vector by numbers. If your verse vector here is representative of some vector A, which, by the way, sometimes you'll see just a vector in like bold letters instead of using that bar notation, vector notation. If your verse vector is vector A, then your second vector, negative A, looks like this. It's the exact same vector flipped in the opposite direction. What if you apply twice the force? What if it's 2 times vector A? The wind is twice as strong. You're driving twice as fast. If this is your original vector A, then this would be what 2A would look like. 1/2 A would be the same vector cut in half. Negative 2/3 A, 2 different things would happen. You would take your original vector, you would flip it over in the opposite direction because the negative, and then the 2/3 would be 2/3 as strong or 2/3 as long. It's very similar to transformation. Very similar to transformation. So here we go. Here's the hard part. Let vector R, notice it's a bold R, and it's kind of hard for me to do bold there. If vector R is 3, negative 2, and if you can't do bold, if you want to just do, sometimes they just do a half vector. That's pretty cool with them. You just want to do something like that. If vector R is 3, negative 2, then vector 5 times vector R would equal 15, negative 10. Can I have that distributed problem? That 5 in front of it makes it 5 times horizontally as long and 5 times vertically as long. Negative 4s is going to do 2 different things. It's going to flip it in the opposite direction to make it 4 times longer. So vector s is equal to negative 1, 5. Then negative 4s would equal 4, negative 20. And you could graph those and see the relationship between it. The first one would be a vector that's 5 times longer. In the same direction. This did not change its direction. Now the second one did change its direction in the opposite way, but it's 4 times longer in the opposite direction. Same vector. That's enough of those. Vector addition. Now we're getting to the good stuff. It says suppose 2 draft horses, and we're actually going to come back and work this problem later. Suppose two draft horses are pulling on a tree stump with forces of 200 pounds and 300 pounds. And you see a picture of that here. This horse is pulling with a force of 200 pounds, and this second horse is a little bit stronger, is pulling with a force of 300 pounds. As shown in the figure below, with an angle of 65 degrees between the two forces. And you want to know what the combined force is. The two forces are represented by vectors A and vectors B. Have the same, let's see, the two forces are represented by vectors A and B. If A and B had the same direction, then the total force would be 500 pounds. That makes sense. This is honestly the worst way to pull this stuff up out of the ground. Because what you've got going on is, since this horse is pulling with 300 pounds in this direction and this one's pulling at 200 pounds in this direction, what's actually happened is they're canceling out some of each other's forces. If you wanted to pull with maximum force, with 500 pounds of force, there's not 500 pounds of force acting on that stuff. If they were in a straight line, let's say they were both pulling this blue direction. You combine them, you put them in a straight line, you're pulling in the same direction, 500 pounds of force is being applied to that stuff. But as is, that's not the case. Because only a portion, this is what's called our resultant force. Only a portion of this 300 and only a portion of this 200 is being pulled in that direction. And I kind of get ahead of myself and explaining the rest of it. However, a total of 500 pounds of force is not achieved because the angle between the forces, and it's not 0 degrees. It's got to be in the same direction. It can be shown by experimentation that one force acting along the diagonal of a parallelogram with a magnitude equal to the length of the diagonal has the same effect on the stump as the two forces. In physics, this is known as the parallelogram law. We know about parallelograms from geometry. We'll fix to talk a little bit more about it. The single force A plus B acting along the diagonal is called the sum or the resultant force. I'm going to say that word a whole lot. The resultant. The parallelogram law motivates our definition of vector addition. So let me explain what they're talking about with this whole parallelogram property. You got this vector B and this vector A, and you're putting these forces together. You could take this vector B and just copy it at the end of vector A up here, and also take this vector A and copy it at the end of vector B. You have a parallelogram. Everybody see that parallelogram? Why do we know the parallelograms? Because they're in the same direction. These two vectors will be in the same direction. They're parallel. And this vector B is also parallel to this vector B because they have the same direction. That is a parallelogram. Opposite sides are parallel. And what this whole parallelogram law states is, if you want to add this vector A to this vector B, the sum or the resultant force, which is what we're looking for, is going to be the diagonal that's drawn from one tip of that parallelogram to the other tip. That's what you're going to get. That's parallelogram law. Let's add one. And there you see it. There's a picture of the parallelogram law. If this is vector A and this is a copy of vector A, this is vector B and this is a copy of vector B. If you wanted to add vector A and vector B together, then you're going to get that diagonal there. Would be what it would look like. What about this diagonal? Would that be the same vector? No, it would not. The directions off? Now with the magnitude, what about that? Would the magnitude be the same? No. So let's actually add some. So which ones? You got the vector 1, 3 plus the vector 5, 2. To add those two together, you simply have to come as 6, 5. 1, 3 plus 5, 2. We went through that whole big spiel, make you think that this is going to be hard. 1, 3 plus 5, 2 is 6, 5. Okay? But here's the part I want you to see. Vector 1, 3, which is right here. Okay, now I wished I would have actually done, there we go. Here's vector 1, 3, and if you actually drew vector 5, 2, which is right here, copied 1, 3 to the tip of that, copy 5, 2 to the tip of that, that resultant vector is that diagonal, that parallelogram. Same thing, negative 5, 3, negative 4, negative 2. If you add those two together, you get negative 9, positive 1. A picture of what it's going to look like when you add it together. I don't know where the other part is. Here, let me draw it. You got the vector -5, +3, which is here. And you've got the vector -4, -2, which is drawn here. If you copy this -5, -3, now how do I copy it? You go from the tip of it, you go left 5, 1, 2, 3, 4, 5, 1, 2, 3. If you copy that on, again, it's going to be parallel to that one. Copy this one here. That resultant would be the diagonal, which is -9. You see -9, +1 right there. You might think that's minor, but it's going to be major here shortly. That's enough of that. So, let's try a few. And we won't spend a lot of time on this. Austin, if R is 3, -2, T is 4, -6. Austin, what's R plus 2? 7, -8. And again, that would be the diagonal of your results vector. Now subtraction, we didn't even do subtraction. I think you can handle subtraction. S minus T, -1, 5 minus 4, -6. Take a stab at that one, Drake. What do you think?
3.
Careful, -1 minus 4.
-5.
-5 minus -6 is +11. Right. Minus be plus. So to subtract two vectors, see the. Now you could add the opposite. Subtraction is the same thing as adding the opposite as well. I don't know why I want to overcomplicate things though. If I ask you to do something like 2R plus 3T, what you're actually doing is making this vector twice as long, making this vector 3 times as long, then adding the two vectors together. 2R would be 6, -4. Plus 3T would be 12, -18. 6 and 12 is 18. -4 and -18 is -22. Any questions? Magnitude of a vector. The magnitude is simply the length of a vector. If I took the vector 3, 4, which is somewhere right in there, and I want to know how long that vector is. We've done that before. The magnitude of a vector, well, how far is it from point A to point B? Here's the best way to find out. Drop yourself a line, draw yourself a little right triangle, and I believe to get to this point, we went right 3 and we went up 4. Anybody tell me the magnitude of that vector? 5. To find the magnitude of a vector, you simply perform the Pythagorean theorem. A squared plus B squared is equal to C squared. Here's the formula. You see where it comes from? The magnitude of vector V is equal to the square root of A squared plus B squared. You'll get very good at doing that in your head. Here's a picture of the one that I just did. Here's your first vector, 3, 4. Drop a horizontal, or excuse me, drop a vertical, draw a horizontal. You've got 3, 4, 5 right triangle. -2, +3. There's a picture of that vector. Somebody do that in your head. Your magnitude of that vector would be the square root of what? This is 2, this is 3, A squared plus B squared, you get 13, root 13 would be your magnitude there. Any questions? Find the magnitude, and of course it's got everything chopped off. Find the magnitude of the vector -6, -2, and again, do it in your head. A squared, this is your A and B. If you actually drew it, -6, -2, this is your A and B of that right triangle that you're trying to find. This is 6, this is 2. 6 squared plus 2 squared, your magnitude of this vector be what? 2 root 10. It's root 40, which splits into the square of 4 times the square root of 10, which is 2 root 10. Finding the components. Now this is where it starts getting a little bit different. Find the magnitude of the horizontal and vertical components for vector B that has a magnitude of 8.3 and a direction of 121.3. That sounds a whole lot harder than what we just did. It's not. Okay. Now we're getting into the connection between what we've been doing. Why is this even in the sine, cosine, tangent chapter? We're about to see the connection between sine, cosine, and tangent in this. Pretty much, we want to know what is that vector. We want to know the components. We want to know the x's and y's of this vector. And here's how you do it. You've got a magnitude of 8.3. The length of this vector is 8.3. And the angle of this vector is 121.3. And if you want to, let's find this angle. I think that would be 58.7 degrees. Does everybody see how we're going to do this? We need the vertical and horizontal components of that vector. The vertical component and the horizontal component of the vector. Isn't that a right triangle? This doesn't even involve law of sines and law of cosines. This is basic SOHCAHTOA. Sine, cosine, tangent. SOHCAHTOA. Let's find out which one we're going to use. In order to find the horizontal component of this vector, we have the hypotenuse. We're looking for the adjacent side. So which one are you going to use? Cosine. Set me up an equation, Seth. The cosine of my angle, cosine of, let's call this x and y instead of what they call it. The cosine of is equal to, I'll move it just a second. Good, adjacent over 8.3. And they call it b subscript x. That's simply the x component of your vector. It's not the reason they call it that. So the x component will equal, x will equal 8.3 times the cosine of 58.7. And you can type that in if you want to. But while you're doing it, let's go ahead and talk about the vertical component. Vertical would be opposite that angle. And you've got the hypotenuse, so that'd be a sine problem. The sine of your angle is equal to the y component divided by 8.3. And to solve this one, bring the 8.3 over, and you've got your y component will equal 8.3 times the sine of 58.7. Now, I use 58.7 there. Honestly, if you'd used this 121.3, you wouldn't have to fool with the positives, negatives. It would have kind of worked out for you. But what'd y'all get for your x component? Anybody get it? And it will be negative. Does everybody understand why? Because we're going to the left. Now, like I said, had I used 121.3, if I used this angle instead of using that 58.7 degree angle, my cosine would have been negative. So it would have took care of the sine for you. Your y value, either way, you're going to get a positive y value whether you use 121.3 or whether you use 58.7. What do you get for y? 7.1. So your actual vector that has a direction of 121.3 has a magnitude of 8.3 is, let me erase this so I've got room, negative 4.3, comma, 7.1. That's the component form. Okay, you're going from magnitude and direction to component form, and here shortly we're going to do the same thing backwards. Let's do another one of those. Find the magnitude of the horizontal and vertical components. Not the magnitude of the whole vector, but the magnitude of the horizontal and vertical components for a vector that has a full magnitude of 5.6 and a direction of 22 degrees. So you're somewhere right in there. There's your direction, 22 degrees. And you have a magnitude of 5.6. And you're wanting to know what is your horizontal and what is your vertical components. Pretty much you're saying this. If a wind is blowing, let me copy that vertical component over here. If a wind is blowing at 5.6 miles per hour, at an angle of 22 degrees, actually that'd be 68 degrees from the north. If it's blowing in this direction at 5.6 miles per hour, how much of that wind is blowing to the east? How much of that wind is blowing to the north? That's what you're finding. You're dispersing that force. And the way that you find that, you have a horizontal and you have a vertical component. To find your horizontal components, and you'll start learning this. And the book shows you the shortcut. It gives you formula, but I want you to know where the formula comes from, and that way you start using the formula on your own without really even memorizing it. The cosine of your angle is equal to adjacent over hypotenuse. The sine of your angle is equal to opposite over hypotenuse. So my question is, to find your horizontal component, will you always do your magnitude of your resultant vector there times the cosine of your angle? Yes. To find your vertical component, will you always do the magnitude times the sine? Because remember how closely related cosine is to x and sine is to y. Same thing. Cosine goes with x, sine goes with y. And we do, and I'll top this one for you. .6 times cosine 22. And 5.6 times sine of 22. And you get the vector 5.19, 2.10. That's component form of that vector. Now you could work it backwards. You could use Pythagorean theorem on these two components, and you should get 5.6. But what that means is, if you have a 5.6 mile per hour wind, 5.19 miles per hour is blowing in this direction. That's how much of it you would feel in that direction. And very little, only 2.10 miles per hour of it's going to be blowing in that direction. You're going to say, but that doesn't add up to give you the 5.6. True, very true. Another one? Actually, we've done enough of that. Well, is this different? No, same thing. Let's skip over. Let's do it backwards. Hang on. It scares me to skip over because something tells me that it's going to be different. Let's see. Your x component should be, let's try to use the shortcut this time. The magnitude of your vector times the cosine of your angle. The y component, from what we just did, should equal the magnitude times the sine of your angle. Let's see what we get there. And so that's your actual vector would be that 40 times cosine. A lot of times they'll leave it like that. 40 cosine 330, and your y component will be 40 sine 330. Cosine 330, 40 sine 330. So 34.6 negative 4. Pretty easy. Everybody good with that? And notice there I didn't use my reference angle. I didn't use 30 degrees. I used my 330, and if you use the 330, it automatically gives you your signs. SIGN sign. So now the other direction. Now they're giving you the component vector, which I don't know why they don't put it in vector bar. -2, -5, and I want to know what direction is that, and what's the magnitude of that. And you can find either one first. Doing the same thing, drop you a vertical, and draw your horizontal. You got a right triangle. This is -2, this is -5. How do I find this angle? Now, this time we are going to find the reference angle. And everybody remembers what a reference angle is. How in the world am I going to find out what that reference angle is? Inverse tangent. Perfect. So I'm going to say the tangent. I'm going to say that's my angle. The tangent of my reference angle is equal to opposite over adjacent, which is 5/2. You can do it as positive because that way you end up with a positive reference angle. Like you said, to find that angle, you're going to do the inverse tangent. Move your tangent over the inverse tangent of 5/2. Somebody please stop that here for me. So theta, we'll just call it 68 degrees. Theta is 68 degrees. That's the reference. So we want to know if we're going in the direction -2, -5, if this is our actual vector, how are we going to find this whole angle? Add 180. So 248 degrees. And they call it, they call that, actually that angle theta. Your angle is 248 degrees. Let me erase everything, just to make it cleaner. Theta equals 248 degrees, which it should be. You're in the third quadrant. That sounds good. Now, what about the magnitudes? Everybody remember how to find magnitude of that vector? Pythagorean theorem. A squared plus b squared is equal to c squared. A and b are negative 2, negative 5. Negative 2 squared plus 5 squared is equal to c squared. The magnitude of that vector is root 29. So you have a magnitude of root 29. That's how fast your wind's blowing. That's your initial velocity. That's all those things. And it's going in a direction of 248 degrees. So really not a lot of new stuff this chapter. It's a lot of the same old stuff. Same thing, but we'll work it just to give you a little extra practice. 2 negative 6, somewhere down here. Can anybody do the magnitude for me in their head? Good. Square root of 40. A squared is 4, b squared is 36, a squared plus b squared is 40. If that's equal to c squared, that means the magnitude of my vector is root 40 or 2 root 10. There's magnitude. Direction, this is 2, this is 6. And you can do the positives. Like I said, if you do the positives, that way your reference angle ends up positive. I just do the positive version. Let's find this angle. I'm going to call it alpha this time, then we'll call the whole angle theta. Let's use 6 and 2 to find alpha, and then we'll use that to find this actual directional angle that we're looking for. The tangent of alpha is equal to opposite over adjacent. So the inverse tangent of 3, somebody tell me what alpha is, please. So alpha is about 72 degrees. What you got? So what is our actual direction? If the whole thing is 360, this part is 72, that leaves me with 288 degrees. So you have a 288 degree vector with a magnitude of 2 root 10. That's direction and magnitude. All vectors have both direction and magnitude. So ready to start doing some word problems. We're getting there. We're getting really close. Dot product, and we'll stop for the day, and that'll leave us with word problems tomorrow. So that'll be a good stopping point. Dot product. You'll find out that when you're dealing with matrices, it's the same thing. Vector is a matrix. You'll learn that later on in linear algebra. When you're dealing with vectors or matrices, there's actually 3 different ways to multiply. We've already talked about one. One method of multiplication is what we call scalar multiplication. Like 3w, you multiply everything by 3. Another type of multiplication is what we're about to start doing is dot products. And then you'll learn later on cross product. We're not going to do, I don't think we do cross products in this class, but later on you'll learn about cross products. Here's how to find the dot product. When you've got a dot between the two, here's how you find the dot product of 2 matrices. The dot product of negative 3, 2 and 5, negative 1. Very easy. Take your first 2 components, negative 3 and 5, and multiply them together. Plus. Take your second 2 components, 2 and negative 1, multiply them together. The dot product of 2 matrices is a number. The dot product of these 2 matrices is negative 17. Find the dot product of those. I think I've heard me ask. Josh? Find the dot product of 2 matrices, multiply the first components, multiply your x components. What do you get, Josh? Plus, multiply your y components. So your dot product here is. And that is very similar to, if you remember, do you remember how to multiply matrices? Kind of done that back in algebra 2, row by column, very similar to that. Now here's your first application of dot product. The angle between 2 vectors, and I'll write this down. If A and B are two non-zero vectors. And what a non-zero vector is a vector that has a magnitude of 0. It's not very long. If A and B are two non-zero vectors and alpha is the angle between them, alpha is the angle between them, then the cosine of alpha is equal to A dot B over the magnitude of A times the magnitude of B. Cosine of alpha equals A dot B over the magnitude of A times the magnitude of B. That's how to find the angle between two vectors. If the angle between the two vectors is 90 degrees, let's think about this. If the cosine of alpha is 0, if the cosine of alpha is equal to 0, the cosine of what angle is 0? Alpha is 90 degrees or 270 degrees. All right. So if you have, well, what makes this 0? This being 0. Anytime, and that's your first, you're going to use that so much, okay, in your higher courses. If your dot product is 0, your angle is 90 degrees. If the angle between the two vectors is 90 degrees, then the two vectors are perpendicular, or here's your other word, orthogonal. Orthogonal is simply another way of saying perpendicular. Why do we need another word that means perpendicular? I have no idea. Okay, orthogonal. If the angle between your two vectors is 90 degrees, and from what I just told you, the dot product would be 0. Anytime you have a dot product of 0, that's going to be the case. The two vectors are going to be orthogonal or perpendicular. We'll work a couple of these problems, then we'll stop. Vector A is the first one, -3, 2, and 4, 5. I want to find the angle between these two vectors. -3, 2, and 4, 5. Your formula for finding the angle between two vectors, the cosine of alpha is equal to A dot B. Find the dot product of the two vectors divided by the magnitude of the two vectors. Raj, find the dot product of these two vectors for me, please. Multiply the x's, multiply the y's, and add them. What do you get? -12 plus 10, which gives you -2. So whatever we got. -12 plus 10, -2. Over the magnitude of A times the magnitude of B. Anybody do the magnitude of this in their head? The square root of 13 times the square root of 41. Good. Don't worry about trying to review those. We're fixing to type this straight in our calculator. So to find out what alpha is, to find our alpha, we're now moving the cosine over. So you're going to have, just type it straight in. The inverse cosine of -2 divided by, I'm going to put square root of 13 times square root of 41. And since I wanted to divide it by that whole thing, make sure you put that whole bottom in parentheses. I think I've got enough there. 94.96 degrees. We'll call it 94 degrees. Or 95 degrees, excuse me. Alpha is about 95 degrees. That's the angle between those two vectors. If you took and graphed those two vectors, -3, +2, somewhere right in there, +4, +5, then the angle between those two vectors would be about a 95 degree angle. Any questions? Second one, do the dot product of that. -5 times 9, 45, -45, 9 times 5, +45, what's the dot product? 0, do we have to do the magnitude on the bottom? No, 0 divided by anything is 0. What's the angle between those two vectors? 90 degrees. Anytime you have a dot product equal to 0, you will always have orthogonal vectors or perpendicular vectors.